Welcome to a walkthrough of GCSE Computer Science for AQA, and we're going to have a look at Paper 2, Computing Concepts from May 2023. So the first thing to begin with is it's really important to ensure that you get the front page correct, because you definitely want to ensure that you get your marks back after you've completed your paper. So do make sure you complete the centre number and candidate numbers accurately and clearly pop on your surname and your forenames as well. And don't forget to put your signature on as well. And you can see it'll give you some basic information on the start, which is standard on the front of most exam papers. You'll be given 1 hour and 45 minutes to do this paper. And you can see that the rest of it is used to be filled in for the number of marks available in each section. You'll also be given some other instructions. So for example, you are not allowed to make use of a calculator, so please don't bring one of those to your exam. And it shows you how to correctly fill in the lozenges for the multiple choice questions as well. So do make sure you have a read of that. And in total, your paper is worth 90 marks. So you've got 90 marks and you've got 1 hour and 45 minutes to complete it. So let's start off taking a little look. Now you will find most of the paper 2s will begin with multiple choice style questions at the beginning. It's always quite low stakes, and then it'll dive into a little more detail as you go further through. So the first one here asks us to take a little look at shading one of the lozenges, and it says the number base 2 is called binary. And in this one, so the first question here, it's asking us to take a little look at a multiple choice question, so we'll tackle it. And the first question reads, the number base 2 is called binary. Shade one lozenge to show which number base is called hexadecimal. So of course we know that hex means 6 and decimal means 10. So 6 and 10 means it is base 16. So we complete that lozenge to show that it would be D for the answer for that one. The next question asks us to shade 2 lozenges this time to show the statements that are true about hexadecimal. So we read through each of the statements. So hexadecimal can represent a greater range of numbers than binary. Well, that's not strictly true. Hexadecimal is easier for people to read than binary. Now, I think that definitely is true because it's much easier to read 2 digits than to read 8 digits, for example. Then hexadecimal is faster for a computer to process than binary. That's inaccurate because hexadecimal gets converted to binary. Hexadecimal is more accurate than binary. Again, no, that is not the case. Hexadecimal takes less space in RAM than binary. No, that would not be the case either. Hexadecimal takes less time to type than binary. Well, it does, because back to our previous reasoning, we just said that it's 2 digits. So it definitely takes less time for a human to type in. Okay, so the next question here says convert the decimal number 171 to binary. Now this is just a 1 mark question. I would always suggest, if where possible, to make sure you put the binary way in line out for yourself. So I would write out 128, 64, 32, 16, 8, 4, 2 and 1. And you could draw it in a table and so on if you wanted to. I won't do that. I'll just see if I can put the number underneath. So again, as always, we're going to start from the left-hand side, and we're going to see if 128 divides into 171, which of course it does. And then we're going to keep adding up along there. So could we add 64 to that? No, we definitely could not. So in this case here, I'm basically saying to myself, what's the remainder from 128 to 171? Well, in that case, if I added... let me take a look. If I added 42 to 128, well, adding 2 would get me to 130, and then adding 40 would get me to 170. So I would need an extra one. So it means it would be 43 would be my remainder. So I know that 64 doesn't divide into 43. However, 32 does divide into 43. The remainder from there would therefore be 11. 16 does not divide into 11, but 8 does, with a remainder of 3. 4 does not divide into 3, but 2 does, with a remainder of 1. 1 divides into 1, and I end up with my binary answer there. 1010 1011. Okay. The next one asks us to convert the hexadecimal number 2D into binary. Now, there are a couple of ways to go about doing this. It says we should show our working, and we get 2 marks for this. So one way would be if you're more comfortable converting it into denary first, then converting your denary number into binary from there. So if we were going to do that, that would be one way of doing it. Now, I personally find it much easier to do this. I split the number out. So let's split it in half. And on the left-hand side, I'll write the binary way in line of 1, 2, 4, and 8. And on the right-hand side, I'll do the same of 1, 2, 4, and 8. And all we're essentially doing is working it out as 2 4-bit nibbles. So the binary number for 2 would be like so. And the binary number for D, well, remember D is 13, so we need to represent 13, which would be 8 plus 4, because that's 12, plus 1 gives me 13. So my final answer that I would submit there is the number that I've got in red, which would be 0, 0, 1, 0, 1, 1, 0, 1. That would be our final bit. And the mark I would be awarded there would be for both parts. I've shown my working out. That should be absolutely fine. Okay, next question. So the next one we've got is a binary addition. So we need to add together the following 3 binary numbers and give your answer in binary as well. Okay, now some people at this point would try and convert these numbers into denary and check their answer and so on. If you follow the simple binary addition rules, you should be pretty good with this one. So in this case, we've got 0 plus 1 plus 1. Well, 1 plus 1 is 2, and we know that the rules are, let's just write them out just to be sure. 0 plus a 0 gives us 0. 0 plus 1 gives us a 1, same as 1 plus 0 gives us a 1. 1 plus a 1 gives us 0, carry the 1 over. So I'll actually write that like so. And 1 plus a 1 plus a 1 gives us a 1, carry the 1. So I can use those rules to remind myself when I'm doing this. So if I've got 1 plus 1, well, that gives me a 0, carry the 1. Now I've got 1 plus 1 again, that also gives me 0, carry the 1 over. I've got 1 plus nothing in this case here, so that would give me 1. Now I've got 3 1s. I've got 1 plus 1 plus 1. Well, 1 plus 1 plus 1 we know is a 1, carry the 1. We get the same thing again because we have 3 1s, so 1, carry the 1. 1 plus nothing else would just be 1. 1 plus 1 is 0, carry the 1, and then 1 plus nothing else would be 1 there as well. So our final answer would be 1, 0, 1, 1, 1, 1, 0, 0. And that should be sufficient to pick up both marks there. Okay, next question. We're on to number 4 now. So we're going to see now if we can convert 16 million bits into megabytes. And it tells us we need to show our working out again. So for this one here, there's a couple of things we can do. Well, the first thing is if we're working in bits, we need to get it to bytes. So the first thing I could do is I could say, well, we've got 16 million. And I'm going to divide that by 8 because that takes me from bits to bytes. I'll make that a little bit neater for you. So we go from bits to bytes. Once we've then done that, so again, if I was going to do that, I'm just doing 16 divided by 8, remember? So that just gives me 2. And then I just carry the zeros, so 2 million. Perfect. So from there, if I'm going to get that from bytes to kilobytes at this point, I would then divide that number by 1,000. So we'll divide that by 1,000 this time. So to go and do that, well, dividing by 1,000, remember, is just the same as essentially removing 3 zeros from there. So that would give me 2,000 at that point. So that's giving me 2,000 kilobytes. And again, if I wanted to do that from that point to then get it to megabytes, I would just repeat that process again by dividing by 1,000 again, essentially dividing by 1,000,000 overall. And overall, once I've done that, well, 2,000 divided by 1000 again would give me an answer of 2. So my final answer would be 2 megabytes overall. Okay, so we divided it by 8 first of all to get it from bits to bytes. We then divided by 1000 to get it to kilobytes, and we divided by 1000 again to get it into megabytes. Question number 5 now. Describe the binary shift that would be used to divide a number by 4. So remember, with binary shifts, we know that if we go to the left, we will multiply a number, and if we go to the right, we will divide it. So because the question says divide, we know that we're talking about a right shift. And then we know that each time we move one position to the right, the number will divide by 2. It will halve. So if we're going to divide the number by 4, that means we need to move to the right again. So our final answer in that case would be, we would shift the number to the right by 2 places. And something like that would be sufficient for you to pick up the marks there. Next one is asking us, when a sound is converted to a digital form, it is sampled. The sampling rate is measured in hertz, and it asks us to define the term hertz. So with hertz, what we're essentially talking about is 1 sound sample per second. Okay, and when we do that, we're essentially saying that it's 1 cycle, it's 1 individual cycle of the wave per second. So I would put that down as my answer. So 1 cycle of the wave per second. There we go. Okay, question 6.2 asks us to work out the size of a sound. Okay, so we've got a sampling rate of 20,000 hertz. Okay, that number is going to be really important to us. And we've got a sample rate of resolution of 4 bits. Okay, and we've got it that it lasts 50 seconds. So it's given us our numbers that are going to be really important to us here. So based on that, we've got to work out what the minimum file size would be in megabytes, so that the unit of measure is really important as well. So we've got 20,000 hertz to begin with. And then from there, we've got, we can do it either way. We can multiply it by the 4 bits first of all, or we can multiply by the 50 seconds. Okay, I'm going to do the 50 seconds first of all. So to do that, very simply, I would just do 5 times 2. So we've got 5 times by 2 is 10. And I'm going to put all the rest of the zeros on, which means we've got 1, 2, 3, 4, 5 zeros to add on there. 1, 2, 3, 4, 5. And then we can just section them off. So that basically gives me 1 million at that point. Okay. From there, we also know that it was based on 4 bits. Well, 1 million times by 4 is pretty straightforward. That's going to give us 4 million. Perfect. Now, at that point, what we now need to do is, because we're working in bits here, we wanted to see if we can get this into bytes, and then we'll figure it into megabytes from there. So what I would do is I'm going to base this on the idea of dividing it by, now there's 2 ways I can do this. I can divide it by 8, or I can divide it by 8,000, because that's going to give me straight into kilobytes there, then I can get it in megabytes directly. So if I divide that by 8,000, well, that's really straightforward to do, actually. 4 divided by 8 gives us a half. So I can put 5 down, or 0.5. We'll move the decimal place anyway. And then I can remove the 3 zeros from both sides. So that leaves me with 5,000, like so. Okay. And then from there, what I can then do is I can do the same thing again, and I would divide it again. And if I'm going to do exactly that same thing, I would get the answer. Now, let me just see if I can show you an alternate method of what we could do there. So what I was saying to you was we could divide that number by 8. So remember, 4 divided by 8 gives us a half. So based on doing that, then, we're going to shift 1 decimal place. That means we're going to be left with 500,000. Okay? Because I've done it that way, I can now just directly do that by 1,000,000. Okay, so instead of doing it by 1,000, then 1,000 again, 1,000 times 1,000 is just 1,000,000. So I can do that, and that'll give me straight, and skipping the kilobytes, I'll get straight to megabytes. Remember, if we do that, we're just shifting the decimal place to the left 6 places, okay? In which case, that would leave us with 0.5 for megabytes. Okay, so we'll go from 500,000 bits, we're dividing that by 1,000,000, because, little side note, we're saying that 1,000 times by 1,000 is 1,000,000, which it is because we get 6 zeros. So we divide that by 6 places, 1, 2, 3, 4, 5, 6. So our decimal point would end up there. So our answer becomes 0.5 megabytes. We've got a blank page. So question number 7, part 1. So we're now thinking about images. So we've shifted our brain from thinking about sounds to images this time. And it's saying that the term pixel is short for picture element. Define the term pixel. So it's asking us, do we understand what a pixel is? Well, a pixel is very simply a single point or a single dot of colour on an image, and we can phrase that in any sensible way that we see fit. So I'll just simply call it a single point on an image. Perfect, that's it, we can move on. So we've now got a 5 by 5 pixel image. A minimum color depth of 2 bits is needed to store the image. Explain how the image in figure 1 can be represented as a bitmap. So this is really asking us, do we understand what bitmap images are? And can we refer to some of the terminology that's being given to us in the question as well? So what we can now say at this point is that the pixels that make up this image would be stored consecutively. So that would be the first point that might be worth mentioning. It also told us in the question about the colour depth. So it's saying we've got a colour depth of 2 bits, 2 binary digits. So that means we can also explain that we understand what colour depth is. Because with colour depth, remember, it's 2 to the power of how many bits? So if we're using 2 bits, it's 2 to the power of 2, which is, of course, 4. So we can have 4 possible colours for our pixels in our image. So based on that, we can start to provide our answer. So we could say, I'll just rub off our notes for the time being. There we go. And in our answer, we can put something like, I might type this one for quickness, and so my handwriting doesn't look quite as messy. And in here, I'm going to type in something like, if we can get the keyboard to show. So in here, I'm going to type something like the pixels are stored consecutively. So that's my first point. So basically that means one after another in memory. And then I'm going to say something like with 2 bits for the color depth, the image can store 4 possible colors for each pixel. So I'm kind of explaining that I understand what we mean by color depth and what that actually means. I would also talk about the image itself, because in the question, remember, it told us that it was a 5 by 5 pixel image. So I would say that the image would store the width and height. And remember, we call the width and height the resolution. So that's how many pixels are making up the image by multiplying the width and height together. And of course, the image would not display whatsoever unless we could store the metadata. So we would say the metadata would also be stored for the image. So we're trying to get across the fact that we understand all of these key different parts about images, about bitmaps, and how they are represented in binary. So I've done those as 4 individual little bullet points there. So 1, 2, 3, 4. You just need to be able to make sure you can pick 3 of those out. and see if you can score full 3 marks on that question. So we're sticking with images now, and it's saying we've got a 10 by 10 pixel image this time, 5 different colors. Calculate the minimum file size. Okay, well, when we're trying to calculate the file size, we know that it's going to be the resolution. So remember, the resolution is the height, which is 10 pixels, multiplied by the width, which is also 10 pixels. Of course, 10 times 10 is 100. And it says that we've got 5 different colors. Now, that does not mean that the color depth is 5. It means, I'll do this in a different color because it's a note for you. It means that it is 2 to the power of something which gives me at least 5. Well, 2 times 2 gives me 4. So 2 to the power of 3, 2 times 2 times 2 gives me 8. Okay? So it means that I need to have 2 cubed, 2 to the power of 3, to be able to get at least 5 different colours, because it gives me 8 different colours. So that therefore means that our colour depth is 3. So therefore we need to tie that into our answer, and we'll say 100 times by the colour depth of 3 equals 300. So for our answer there, how many bits would be stored? It would be 300. Okay, so just a top tip for that one is the colour depth is not how many colours it can store, it's what number is 2 to the power of to get at least that number. 2 squared, 2 to the power of 2 is 4, so that wasn't enough, so it had to be 2 cubed because 5 fits into 2 cubed, which is of course 8. So now question 7.4, we still are on images, and this time it's talking about compression and run length encoding. So we're now thinking about compression. The first bit in each byte of the bit pattern represents the colour, and the remaining 7 bits of the byte represents the number of pixels in the run. Okay, so the image has a run of 60 black pixels, followed by a run of 30 white pixels, and it's represented in figure 2. So what they are telling us very clearly there, in fact, is, if I just highlight this up here, they are telling us that this digit here represents the fact that it is black, okay? And they are telling us that this number here, just to there, is representing the number 60. And they are telling us that this digit here is representing the fact that the pixel's on, so it is white, and they're telling us that this bit here is representing the binary number for 30. So that makes perfect sense through their demonstration for us. So what they're then doing then is going to ask us a question using the same run length encoding method. Give the bit pattern for a black and white image that has a run of 64 white pixels followed by a run of 15 black pixels. Okay, so the first thing to do here is just remember that they've treated this image where it's been split in half. So let's do exactly the same thing. And I'm going to start filling this in. Well, they told us previously before where they were using white, it meant the pixel was switched on. They were using 1. So they want 64 white pixels. So white is represented by the number 1. So we'll fill that in there. And then we've got to use 7 bits to represent the number 64. Well, that means that if we put our column headings here, it means this would be 1, 2, 4, 8, 16, 32 and 64. So to represent 64 like that, that should be a nice easy job. We put a 1 followed by the remaining zeros. So that gives us 64 white pixels. We've done that bit so far. Perfect. Let's now move to the other side then. So they want us to do a run of black pixels where we know from before that black pixels was represented where it was turned off. So we know that for black pixels we will use 0. And it says a run of 15. Now let's do the same thing so we don't make a mistake. We've got the time in the exam to do this. So we'll put our binary weighing line, our column headings, 32 and 64, and double check the number. It wants us to do 15. So if we're doing 15 here, we're going to write 15 up. Well, 15 is 8 plus 4 plus 2 plus 1. And we'll backfill the zeros to make sure we don't have any blank spaces. And then we've got our completed answer to pick up 2 marks. We would get 1 mark for that side and 1 mark for that side. Question 8 now asks us to move on to thinking about hardware and define the term hardware. Well, we know hardware is any physical component of a computer, so we can phrase that in any particular way that makes sense. It's only worth 1 mark, so we clearly don't need to give an example or anything because they haven't asked that of us. So I would literally write something along the lines of a physical component of the computer. Let's type that in again, just so it saves you having to read my messy handwriting. Let's try that. So a physical component of the computer. Okay, perfect. Next one then. So we're now being asked to describe the role of each of the following components of the CPU. We've got 3 of them. So the first one is asking us about the clock, the second one is the control unit, and the third one are registers. Okay, well let's have a little go of doing that one to begin with. So we'll just draw out a little text box. So what does the clock do then? That's what we're being asked here. So the clock, remember, is a way of trying to regulate the timing and the speed at which the computer, the CPU, can carry out operations. So I'm going to try and phrase that in some kind of way like that. So I'm going to say it regulates the timing of the CPU / computer. Try typing that properly. Computers, operations / instructions. Okay, I'm happy with that. It's only worth 1 mark. That seems like it makes sense. The control unit. Okay, so with the control unit, we know that the control unit essentially is trying to, or certainly at GCSE level, we can say it basically coordinates the actions of the CPU. It actually does a couple of other things as well, because it also performs part of the decode part of the fetch code execute cycle. So I could go with any of those things in actual fact. So I could say that it coordinates the actions of the CPU, or I could say, it's only worth 1 mark, remember, so I'm just going to go with one or the other, or I could say that it decodes instructions once fetched from memory. Again, either of those would be perfectly valid answers. And then registers. So what do registers do? What are they exactly? Well, we know that registers are very small, very fast pieces of memory that are on the CPU. What is the purpose of them? It means that when a data or instruction is being fetched from memory, that it actually gets stored on the CPU, so it can be used during that fetch to code execute cycle. So I'm going to phrase it as it holds data or instructions during the fetch, decode, execute cycle. It doesn't ask us for examples. So there we go. It doesn't ask us for any examples, so we don't necessarily need to dive into them. So there we go. Just have a quick check back of our answers there. I'm happy with those. They make sense. We've answered the question directly. We should be good to pick up 3 marks in that instance. The follow-up question from there for 8.3 says, give one reason why the CPU with 2 cores might perform faster than an equivalent CPU with just 1 core. So why would a CPU with 2 cores perform faster than a CPU with just 1 core? Well, essentially, we know that cores can independently fetch, decode, and execute instructions. They are essentially, think of it like splitting your brain into 2 separate parts and being able to do things simultaneously. So the idea that they can do things simultaneously at the same time, we call that in computing, you can also call it parallel processing. They can be done alongside one another. So we would phrase that as something like that for our answer. Let's see if we can type that in, shall we? So we'll say that the CPU with 2 cores can process 2 times more instructions, and then we can go with at the same time or simultaneously, okay? The same time. There we go. Nice, straightforward way, showing the examiner we understand exactly what cores are and what their purpose is. Question 8.4, then still related to hardware, moves on to asking us to define the term volatile memory. Volatile memory. Now, we need to cast our mind back here and think, well, what does volatile mean? Well, volatile memory means, or something that's volatile in computing, means that when it loses power, it does not retain its contents. It does not remember the programs or the instructions that it had there. So define the term non-volatile, well, that must mean the opposite. It means that it will retain its contents when power is lost. Okay, so we can phrase it as something like that. So non-volatile memory means it will retain contents when power is lost. There we go. Perfect. Now we need to give one example of a type of volatile memory in a computer system. So be careful here. We need to read the question because it's just went from asking us about non-volatile to volatile this time. So we know that when we're talking about non-volatile, retaining contents, we're talking about secondary storage, for example. When we talk about volatile, we're talking about elements of primary storage. We could be talking about parts of the CPU. So we could give example answers here. There's only one needed, but sensible ones. The most obvious one given our definition would be RAM. We could have also mentioned cache. We could have mentioned registers. Anything like that would be volatile memory. I'll stick with RAM though. Explain why secondary storage is required in a computing system. Well, this relates back to the first question just here, doesn't it? Because it's asking us about retaining its contents. Why do we need memory or storage that will retain its contents? Well, we need to be able to store things. What do we need to store? We need to store data. We also need to be able to store files, don't we? When do we need to be able to store them? When power is lost. Okay. Now, when power is lost could mean just that, if we had like a power shutdown or we lost power unexpectedly, but it also means when we just want to shut our computer down and come back to it another day. So when it stores our data, stores our files, stores our software, however you want to phrase that is absolutely fine when the computer loses power. Okay, they are your two key bits. What does it store and when? That's where our 2 marks would be made available there. We now need to see if we can define the term software. All right. Well, what is software? What does software do? We're trying to get our brain into that part of the specification now. So I guess we could probably say software is some form of program which can be executed by the hardware on the computer. That would make sense. So we could say it is a program which can be executed or can control the hardware. Because remember, some software doesn't necessarily have to be application software. We could be talking about utility software, for example, that can help us defragment a magnetic hard drive and so on. Define the term system software. Okay, so we're diving into software types now. So we've got system software with a follow-up question on application software. So let's get our brain in that sort of space then. So system software is when we talk about software that can somehow help with the function of the machine itself, okay? So it can control or manage the computer. Now, because this is only a 1 mark question, That would be a valid answer to get our mark. We could have also said it manages the hardware. It can enable the computer to function, because we could be talking about like operating systems and so on. So there's lots of valid answers we could put there. The follow-up question on what is application software, can we define the term application software? We would say that that is software which is predominantly based for end user tasks. Okay, again, it's not asking us for an example, but if we were to give an example, we're thinking about things like word processing software. We're talking about things such as web browsers and email software and things like that. That's our application software. So from there, we're now going to have a go at explaining the role of main memory in the execute stage of the fetch execute cycle. Right, we need to switch our brains away from software. We're coming back to think about elements of the hardware again. What happens during the execute phase of the fetch execute cycle to begin with? Well, once that instruction has been fetched, the CPU has decoded it. It's trying to understand what we need to do with it. That will be one of two things. It could be that two numbers have been added together and we need to go and store that result somewhere. That would be in memory. So it could be that the result of a calculation needs to be stored. It could be that we need to store the result of a logical decision. Think about when you write code and you write if statements, it could be the result from that. It could be that we need to get another instruction. It might be the next thing that we need to go and fetch. So with this one, we could say something along the lines of, might be easier if we type this one out. Let's do that. So we would say something like data that is required may be fetched from the memory. So that would be one valid thing that we could put there. We also said that it could be the result of a calculation, for example, could be stored in memory. Okay. So there's two valid things that we could put down. It was worth 2 marks. We have a sufficient amount there to score the marks. We now need to describe 2 stages of the fetch execute cycle. So we know that it goes fetch first, then we've got the decode part second. So let's do them in turn. So what happens during the fetch phase? Well, what are we fetching? We're fetching an instruction or some data from memory to the CPU. So let's put that down. We fetch the next instruction. It's all about getting those keywords in, or data from memory, from the RAM. So we're fetching that. Where are we fetching it back to? The CPU. Then what happens? The decode stage is the bit where the instruction is actually being decoded. It's figuring out what it needs to do with it. Okay, so the decode stage is just the instruction being decoded. Is decoded, and what does that mean? To really spell it out for them, it means that we are working out what is to be done. And again, to make that really make sense, that could be to carry out a calculation. It could just be that we've got a number, we need to store it in another memory location to use later. Could be lots of possible things. All right, so now we're moving on from looking at hardware and so on. We're going to start talking about truth tables. So we've got a truth table for an XOR logic gate. Now remember, an XOR means it's exclusively OR. An OR is where it's one or the other. It's A or B. So that means that it's only when one input is a 0 and the other is a 1, or vice versa, do we get a 1 to be the output. So in that case, 2 zeros would present us with a 0, false. 0 and 1 would give us 1. 1 and 0 would give us 1, and 1 and 1 would give us 0. Remember, in a normal OR gate, that would have also given us a 1, but this isn't a normal OR gate, it's exclusively OR, so it's only those two ones there. Now we've been given a logic circuit to state the type of logic gate labelled in G1. So G1 here, do we recognise that gate? Well, it looks like the letter D. It has 2 inputs and 1 output, so that must be an AND gate. And then, let's have a little look here. My prediction was, is it going to ask us what G2 is? Well, it doesn't look like it is just yet, but let's take a look. We need to write a Boolean expression to show how the output D is calculated from the inputs A, B, and C here. Well, we need to recognise that we've got the AND gate and we've got an OR gate there. So it means that to write an expression for this one here, we need to basically start with what the output would be, so it gives us D equals. We can then try and think about the order of precedence here. Okay, now the order of precedence, if you can't remember it, it always goes with any brackets first, then any NOT gates, then AND, then OR. Now I'm going to do that in the same fashion here, so I'm going to start with the AND gate first of all. So we've got D equals A and B. So I'll write this in normal plain English, then I'll put it in the AQA dot notation as well. So we've got A and B, and then the output of that is ORed with C. So we go with OR C like so. Okay, now in this case here, I don't need to add brackets. I could add brackets if I wanted to around A and B, but why do I not need to do that? Because A and is higher in the order of precedence, so I don't actually need to do that. So the alternate way of doing that, I'll just do it in a different colour so you can see that, it would have read that D equals A dot for AND, B plus C, because plus is OR, remember. You could use either one of those, so I'll put slashes between them so you can see the difference there. Perfect. Now, just a little tip on that. There are kind of ways you can write that. I would recommend that you stick with this one, okay? Just on that note, just kind of thinking of exam technique as we talk about this, I would stick with the dot notation. Generally speaking, it's okay to write those words, but just on the off chance that they didn't allow it, I would always go with your dot notation, even if you just need to write it out first of all, but most students often seem to be okay with that. Okay, so now it looks like we've got a question around the idea of high-level, low-level languages and so on. So we're moving into that kind of topic area, trying to get our head switched to that area. And then we're also thinking along the lines of translators and compilers and so on. So we're trying to flip our brain into this space now. So figure 4 shows us 3 programs that add 2 numbers together, output the results. The programs are written in different programming languages. Okay. Identify the type of language that's being used for each program. All right, so we've got to fill in letters in here to try and show which one is which. So x equals 14, y equals 3, z equals x plus y, output z. That looks very pseudocode / Python style. It looks like somewhere in between them. So based on that, we know that things like Python and C# and all those other programming languages, they are what we call a high-level language. So therefore, it looks like A is a high-level language. B is using what we call mnemonics, LDR and ADD for add and STR for store and OUT for out and so on. Okay, so basically with that, that is what we call, one example of it is Little Man Computer. And that is what we call an assembly language. So assembly language is what uses these mnemonics. So that means that B is our assembly language. C looks like it is plain binary. And we know that all computers understand as binary, and therefore that gets translated into binary as what we know as machine code. So it means that C is being represented with machine code there. Now, it asks us then to state one advantage of writing programs in assembly language instead of a high-level language. Well, looking at assembly language there, in column B, it actually looks a little bit tricky in comparison with what we're used to. Okay, but it does actually have some advantages. So some advantages of that would be things like programs that have been written in an assembly language can actually run faster, and they use less processing time because you can directly address the CPU. Okay, they can directly interact with different bits of hardware. So there's actually lots of advantages of that. So I'm going to put something like that down. So I'm going to say that they can, programs, I'll use full sentences. So programs can run faster. So that would be a good example because they use less processing time. Okay, we've got another multiple choice one now. Fantastic. So shade one lozenge to show which statement is true about program translators. So looking at this one here, a compiler translates all the original program code before execution. That sounds like it would be accurate. Yes, let's double check the others just in case. So compiled code still needs the original program code execute. No, that is not true. It gets compiled into an executable file. Compiled code executes more slowly than code being interpreted. Nope, that's not true. The interpreter takes a little bit longer. And interpreters generate machine code directly. Nope, I don't think that is true also. So I'm going to go with A for that one. And notice that even though we thought A was correct, we still went through and checked the other answers just to make sure we haven't made any sort of silly mistakes. All right, changing topic again this time. So we're now looking at networking, and it's asking us to describe two differences between a PAN, a personal area network, and a WAN, a wide area network. So we know that a personal area network is centered around a person. So we would phrase that as, let's go with a PAN, is around about, I'm just noting this slightly shorthand for you here, somewhere about 10 meters. Okay, whereas a WAN is what we call a large geographical area. So I'll phrase it as just that, a large geographical area. We could be talking about over a mile, for example, in that instance there. A second difference, there's quite a few actually that we could choose from here. Let's see, a PAN would only connect very few devices. A WAN would connect lots and lots of devices together. A PAN would only be used by one person, whereas a WAN would be used by multiple people, multiple organizations, and so on. A PAN's using a person's hardware, their own individual hardware, whereas a WAN's using external hardware and things. So there's lots of things we could put down as our answer there. I'll just go with the person one. So PAN is going to be for like a single person. And we said that a WAN would be for multiple people / organizations. Now, if this were a real exam, I would probably take a little bit more time to make sure my answers were nicely formatted. Just conscious of the length of the video for you as the learner, though. So, question 13.2 this time. We need to shade two lozenges this time. Let's read the question carefully. We don't want to drop any silly marks due to poor exam technique. So shade two lozenges to show which statements are true about LANs. So a LAN always uses the Ethernet protocol. That's not strictly true, is it? A LAN always uses wireless technology. No, because it could be using wired technology. LANs are usually controlled or owned by a single organization. Now, we know that is true. We just said the opposite for a WAN before, didn't we? LANs connect a maximum of 150 devices. Nope, you will have more than that connected in your school, no doubt. And LANs cover cover one room, building, or site. Yes, that is definitely true. Because it could be a house, a very small office. It could be a school site, for example, or a small business. So you've got 2 there, feeling very confident that we've got them both correct. State 2 differences between a bus and a star topology this time. Okay, so 2 differences between a bus and a star. I might type these ones just to see if we can get it looking a little bit neater perhaps. So between a bus and a star, well, we know that a bus is a single cable in the center with that like backbone idea. And we know that that causes quite a few collisions and stuff. We know that schools and businesses and organizations wouldn't use a bus. They would use a star topology due to the disadvantages that a bus brings. So let's see if we can describe a couple of differences here. So we could say that a bus has all devices connected to a single cable, which I called the backbone there. Whereas a star topology would have them all connected, would have all devices connected to a central device, usually a switch these days. So that would be a nice one to go with to begin with. There's lots of other things that we could state there. So like second differences would be that a bus has a central point of failure with the single cable, whereas it's very unlikely that a switch is necessarily going to go down. So with a star, if one device fails, all the rest will still operate. Of course, that doesn't quite apply to the switch, but in general, the likelihood of a single device, of the switch going down, is very low. A single device going down is much higher. So there's lots of different things. There's lots of other things we could go with if you weren't as confident in one of your answers. You could talk about a star having less data collisions, certainly less frequently, whereas a bus, they're going to be much more frequent due to that single cable, all the traffic, etc. So moving on with a bit more networking. So HTTP is an example of one network protocol. Define the term a network protocol. Well, an alternative word for protocol is simply a rule. So network protocols, what do we mean? They are simply a set of rules. So that would be my first thing. So a set of rules, because there are multiple of them, which allow, what do they allow? Well, they allow all of our devices to actually communicate with each other and transmit data between them. So allow devices to communicate / send data. Send and receive data, I guess. There we go. So I've got 2 key things in there. A set of rules would be 1 mark, and then allows the devices to communicate would be my second mark there. And now the application layer and the transport layer are 2 of the layers within the TCP IP model. What are the names of the other 2 layers? So it's given us them, the first 2. So it's given us application and transport. And I always remember it as ATIL. Okay. You can also have N at the bottom as well. So that means that I would be naming one as the internet layer, and the other one would be the link layer. Okay, and like I say, you could have the network interface layer for the bottom, or you could have said the network access layer as well. Quite a lot of them will have a link layer at the bottom. Lots of possibilities. Great, okay, feel confident that we have all of those there. Now it looks like question 14, we are having a look at databases. Okay, so the teacher uses a relational database containing 3 tables. So we've got book copy, student and loan. I think those names in bold are going to be relevant to the question here. So the first question then, Shade 2 lozenges that show which of the following statements are benefits of a relational database. Okay, so all the information can be stored in one table. No, that would mean it's a flat file database. B, redundant data is less likely to be stored. Yes, that's one of the key purposes of a relational database. Tables don't need primary keys. Nope, that is unfortunately lies. There are less likely to be data inconsistencies. Yeah, that again is really important in databases. Next up, state one field in the loan table that is a foreign key. So remember, a foreign key, we're trying to ask ourselves, can we remember what a foreign key is? Well, a foreign key is when you've got a field in a table that is a primary key in another table. So this asked us about the loan table. So we've got the loan table here. Obviously, the primary key would therefore be the loan ID. Which things in here are going to be primary keys in other tables? Well, looking at the other tables, we can see that in the student table, student ID would be one of them, and in the book copy, copy ID would be them. So they would be our two answers there. So we just need to state one of them, state one field. So I'll go with copy ID, and I will write that exactly as it appears in the question. I will not change it. I'll keep capital letters where they are. I won't change anything about it because I'm not going to give them any chance of taking an easy mark away from me. Okay. State the most suitable data type for the field deposit paid field in the loan table. All right, well, deposit paid in the loan table looks like it's going to be based on money, and because of that, it looks like it's based on decimal numbers. So because of that, there are a few possible answers that we could put down there. A sensible answer would be what we call decimal numbers in our programming, which is either a real or a float. They mean the same thing, really. A real or a float. Okay. Generally speaking, it would accept decimal because you can actually have that in a database. Currency is also normally one. I would stick with what you know best from your programming, which would be a float. Okay, so it looks like they've repeated the table for us again, just for our convenience on the printed paper. So year 11 must return their book. Okay, so using the database, we've got to write an SQL query that lists all the loans for students who are in year 11. The query must only return both names of the student, the ID of the book borrowed, the deposit that was paid. And it says the results must be in ascending order based on the students' last names. Okay, so there's a few bits going on for this one really here, isn't there? So the first thing we need to do, let me just grab the keyboard and we'll start typing this, I think. So just to make sure we've got the question kind of visible at the same time, well, we need to select some information here. So let's do just that. We'll use a select query here. And what is it we need? So let's go back through. It needs both names of the students. Let's check the table again. So for the student, we can see that we've got first name just here, and we've got their last name as well. So let's use those exact field names. So we want to select the first name, which was written like so. And then we need their last name, which was also written in that sort of camel case style. What else did we need? It tells us that we also need the ID of the book borrowed. Let me just check that field again. So when they are borrowing something, that is called the copy ID. And we also needed the deposit that they have paid. So we would want the copy ID. And we would also want the deposit that they have paid. Deposit paid. Where are we selecting that from? Well, from comes next. And we're selecting that from the student and the loan table, aren't we? So we're going to select that from student and the loan table. Okay. And then what was our criteria there? Well, we basically want to match up any student's ID against the loan that they've made. So what we need to do is put where. This is going to go in our criteria here. And our where is going to be where the student ID, so we will say student ID, so we can grab that field from that table, equals from the loan table, the student ID. So loan.student ID from there. So that's going to compare the student ID from those two tables. Do we have anything else? Yes, we need their year group for year 11, remember. So, and year group is equal to 11. Now, what was the final thing we've been asked to do? I've just noticed I've got a typo on year group. We'll keep them exactly the same. Remember, always checking back to our tables to make sure we've got them exactly as is. So year group, again, use the same sort of thing. So based on that, what was the last thing we've been asked to do? It says they must be in ascending order. So to do the order, we say order by. And what are we ordering it by? It's asking us to order it by their last name. So we'll do that, last name. And it's asking us for ascending order. So we put A, S, C for ascending. Okay. And that would give us a complete rundown for the marks there. So we get the marks. We've got the select clause there to begin with. We've got the from. We've got the where. We've also joined the two tables together to be able to pull the information from both of them. And then we've also got the order by bit. That should be enough for us to secure all of the marks. No problems at all. There are alternate ways we could have done that. We could have used inner joins and so on. But I actually think that is pretty straightforward. Nothing overly complex for us there. So the next one says Barry Tucker has returned their copy of the book Python Basics. Complete the SQL to delete the loan record for the book PB002. Okay, so what do we need to do then? Well, we need to delete from, it's going to be the loan record. So we're deleting from the loan table, aren't we? So we're going to delete from the loan table. What is it that we're going to be deleting there? Well, it's going to be the criteria where the book PB002, and we need to get Barry Tucker's ID no doubt as well. So we're going to delete the one here where copy ID was equal to, now this is a string, so we're going to put it in speech marks, so PB002. And don't forget the other little bit here, and we'll do that in capital letters. And we need Barry's student ID. Okay, so because we don't want to just delete that book for anybody, do we? So we'll say student ID equals, and I need to go and get Barry's student ID. So we'll come up to the loan bit there. Let's have a little look. So we can see Barry Tucker's is there, TUC004. So let's go back to our question and we'll just fill that there. And again, that is a string, so we shall treat it as a string with speech marks, TUC004. There we go. That's our 2 marks for that. Okie doke. Perfect. We're getting there. And then we come to question 15 this time. All right, a little bit of a beastie one, this one, isn't it? So let's see if we can see how we can approach this. So question 15 is talking about wearable devices such as smartwatches and fitness trackers and so on. And it's asking us to discuss the benefits of collecting personal health related data, data privacy issues that would be harmful in this instance, and then legal issues that would relate to keeping people's personal data as well. Okay, now what's important to remember here is how this question is marked, okay? So if we just have a really low level answer, we're going to be in that 0 to 3 mark territory. If we have a decent explanation, we've got descriptions of like some privacy issues, some legal issues, we're going to be in that 4 to 6 territory. Similarly, if we give some really good points about all 3 of those bullet points, and then we give a nice summary at the end to say why we think this is a good or a bad thing, we're then going to be in that top level, level 3, and we're going to be entitled to 7 or 9 marks here. Now, what's really important is we need to give a really logically structured answer, and we need to consider a range of relevant points. So I'll show you how you could approach this kind of answer. Okay, so I'll just map some bits out for us to begin with. Let's do just that. So some things that we might want to include. All right, well, first of all, some benefits. Let's talk about some benefits of storing this kind of data. Well, first of all, it means that we can keep track of our health goals. Yeah, that's probably one of the main reasons for it. So keep track of health goals. Why else would we want to do it? Well, we would want maybe to use it for motivation. So these are the good things, yeah. What else would we want? We'd probably want to share our data, wouldn't we? People love sharing screenshots and things, and again, used towards that motivation thing. Why else would we want to do it? Surely people create businesses out of this. We see new apps and things come up all the time. So we could go in the direction of saying business opportunities. Okay. There's probably loads more things that we could talk about in there as well. Let's talk about, what was the second part of the question now? Data privacy issues. Let's talk about data privacy issues then. What issues might there be? Well, I guess like people may not be aware of how much data is being collected. So that might be one potential issue. What about if a company got hacked? That would be a problem, wouldn't it? If a company were to be hacked, this would cause major issues for the customer. There's lots of other things we could say as well. I guess some people might find their some data may be sensitive / like embarrassing for some people, potentially. And there's lots of other things. I'm just coming up with ones off the top of my head here. We'll then bullet point a few legal issues that we could discuss as well. All right, well, obviously, let's say if you were letting companies or apps collect your data, what happens if those businesses were outside of your country? So that would go against the GDPR, the Data Protection Act, okay? It means that they might be able to share that information without your knowledge because they might not have the same rules and laws as we have here. It can be unclear whether consent has been given, or it might have been given without actual knowledge of it. Has been given... people might just not understand sort of legal terminology and stuff, so that could be a potential issue because it still becomes binding. We could have sort of like some future implications, like what happens if the business gets sold, who controls the data then? So we could mention potential future implications. How long do they keep our data if we leave the app but forget to close our account and stuff like that? So how long do they store the data for? Because we know it shouldn't be an excessive amount of data and only held as long as needed. So there's a few points that we could raise there. Now you can see in terms of exam technique, what I've done is I've bullet pointed out some things that I could talk about. I would then need to form a discussion within my answer covering each of those different points. And I can talk about the advantages and disadvantages of each of those different things I've covered. And then in turn, what I would then want to do is summarize at the very bottom. I would then want to come to the bottom and say something like, let's come down there so we can see, in conclusion, fitness apps and trackers are really helpful for people because of X, Y, and Z, and you can fill in the gaps there. However, there are many issues associated with doing so, and in turn, and you can give like an answer to that bit as well. Okay, and then you can give your final answer. I think overall, weighing up the benefits and drawbacks. Fitness apps are great to help people become fitter and stronger and lead a healthier life or something. Okay, I'm just kind of coming up with it off the top of my head. So the key things are, can we bullet point our answers out to begin with? Can we create a coherent answer that flows in a logical manner? And then at the end, can we give a nice, clear little conclusion about what we think? Really with that bit, you can't really be right or wrong. It's more just kind of giving a sensible response. What's your opinion? And then just kind of weighing up all the bits that you've come to. So it's kind of come to a little conclusion, a little evaluation. Because generally speaking, what we're being marked on here is something along the lines of our knowledge, first of all. So what do we know about the issues that have been raised in the actual question? Then we need to apply it. So the application. The application means, can we apply to the actual scenario you've been given there? Okay, and then, so talking about fitness trackers and apps and so on, and then the end little bit is our evaluation. Okay, have we been evaluative in our comments throughout? Have we give a conclusion towards the bottom and so on? And if we've done that, we've got a really well-balanced, coherent answer to be able to present. Okay, let's have a look at question 16, a shorter one, thankfully. So define the term cyber security. Okay, well, cybersecurity, what are we talking about? We're talking about sort of like protection of our networks and our systems from attack. Okay, so we could phrase it as something like that. Let's quickly type that one out. So we'll say something like protecting systems / networks or technology or anything like that from attack or damage. And a nice phrase you could put in there is unauthorized access. That's always one of the key phrases we see time and time again, preventing unauthorized access. And one way to gain unauthorized access is malware, isn't it? So it's asking us to state one type of malware. Well, there's lots of different types of malware, malicious software. And one example, the most common one, no doubt, would be a virus. We could have also said things like, just noticed that U looks really dodgy. Why don't I fix that for you? There we go. So yeah, we could have said like Trojans and spyware and etc., etc. Lots of different things we could put there. And then we've got another 9 marker, another big question. So network manager of a new computer games company, AQA, is configuring the network. All right. Discuss the potential impact of the following threats. So weak and default passwords, misconfigured access. So it's asking us, do we understand about cybersecurity threats on a network? And again, how can we apply it now? Everything I just said in the question 60, was it question 16 at the very start? No, question 15 here. Everything I said about exam technique there applies to this question. It doesn't matter about the scenario. So what do we need to do? We need to give some key points. We need to cover the knowledge bit, don't we? We need to plan out our answer. It's worth 9 marks. That doesn't mean 9 minutes. You want to spend about 15 minutes here. Okay, that gives you about 5 minutes for planning your answer, 9 minutes for answering it, and 1 minute to go back through and read it and make sure you're happy with it. Okay, so we need to get some knowledge in there. What would the repercussions, for example, of weak or default passwords be? Well, having weak passwords, what's the downside of that? Hackers could brute force it, couldn't they? They could brute force your password and find it out very quickly. Default passwords, they could be stored in a big dictionary, so they could be found almost instantly. What would the implications of misconfigured access rights be? Well, if people don't have the correct access rights, they could get in as a network administrator and do damage from the inside of the network that way. Unpatched or outdated software. Again, that kind of speaks for itself, doesn't it? If the software is unpatched, we've seen this happen in the real world, then it means that it becomes vulnerable to hackers. Hackers can exploit those known weaknesses, find a backdoor into the network, and can bring it down. We've seen that happen in hospitals. We've seen it happen in airports and things. It happens quite frequently, more than it should, in fact. And it's about being able to say these different things. And it tells us in our response, we need to say how these threats can be exploited, which I've just given you some examples of, and how they could protect against them. So how can you protect against a weak password? So for passwords, we could therefore say that we can enforce a stronger password policy. So you could have a password policy. Great. Okay, what else could we do? We could make sure that default passwords are changed on first login. That means anybody that ever logs into your system has their own custom password immediately. Okay, we would then work through each of these different bullet points and try and talk about them. So access rights. I'll just put AR for short, access rights. I'm planning out my answer here. So access rights, how can we deal with misconfigured access rights? Well, one thing we would have to do is be able to sort that out very quickly. So we would have to have like some kind of like application of who gets assigned which access rights at which time. These would often be reviewed regularly as well and make sure that they are acceptable for like the network administrators and so on and people who protect the network. You could give read-only access. That would be a good example. So you could have read-only access where needed. So if people need to view things, great, that's fine, but they can't change them, can't overwrite them. How do we deal with unpatched software, outdated software? Well, I suppose the sensible answer there is update it. Yeah. So we could have regular updates. This would be like a network policy kind of thing, wouldn't it? So having regular updates, we could put like network policy to enforce that. Could be automated. Put automated updates, etc., so that they can't be forgotten about. Lots of simple common sense answers there, I think. Okay. Yeah, and then again, from there, you would just try and bring that together in a coherent way. And again, at the end, you would give a nice little conclusion. It's really important that AQ aware, if we're going to phrase it as that, keep all their software up to date. They enforce these policies that we've talked about to ensure that these threats cannot be exploited by cyber criminals, etc. And that is it. That's the end of the questions. So hopefully that's been a good way of kind of taking you through the full 2023 paper 2 to show you how you can go about securing full marks. And of course, questions can be phrased in different ways, but hopefully that's been quite useful for you. And what we'll do is we'll provide the link to this paper so you can take a little look through it as well and compare it to some of your answers. And as always, if you've got any questions or queries or anything, pop them in the comments and we will see if we can get back to you as soon as possible. Hope that's been useful and we'll see you again soon.